To learn the theory of general relativity, let's conduct a thought experiment. Let's imagine that I am holding a ball in a lab in outer space. Right now the lab is not accelerating, so I will feel like how outer space would feel, no net force is acting on me. This means that if I push my ball, the ball will move in a straight line and in constant velocity, following the laws of inertia. Now imagine a lab on the ground of the earth, where now I feel a force pulling me downwards, sticking me to the ground. If I let go of the ball now, it will fall towards the earth, and we call this the force of gravity. Now let's go back to outer space, and let's imagine that I put rocket boosters on the base of the lab, so it starts accelerating upwards. As it accelerates upwards, I am pushed to the ground of the lab, and I feel a downward force. In reality, the lab is accelerating upwards and pushing up on me, but in my perspective, I feel like I am being pulled down onto the floor of the lab. If I let go of my ball now, it will look to me as the ball is falling down to the floor of the lab. In this case, if I suddenly wake up in the lab with no way to look outside and the lab is accelerating upwards, I will feel a downward force towards the floor of the lab, and I will have no way of telling whether I am in a lab in outer space that is accelerating upwards or whether I am in a lab on the surface of the earth where I am being pulled down by the force of gravity. Finally, let's imagine that the lab is falling down close to the earth. This would mean that the lab is free falling towards the ground. In this case, even though we are falling due to gravity, inside the lab, everything behaves like it would in outer space, in a lab with no acceleration. So if I push my ball, it still moves in a straight line and in constant velocity, with no external forces acting on it. This means that my frame of reference inside this lab in free fall is an inertial frame of reference, where no net forces are acting on me. Now we see that case 1, the case of the lab in outer space with no acceleration, and case 4, the case of the lab falling towards the ground in free fall, basically seem the same if I'm inside the lab. We also see that case 2, the case of the lab on the ground of the earth, and case 3, the case of the lab accelerating upwards in outer space, also feel the same if I'm inside the lab. When Einstein thought of this, the only conclusion he could come to was that gravity is a fictitious force. What is a fictitious force? In case 3, the lab is accelerating upwards. There's a force pushing the lab upwards. But I feel like I am being pulled downwards onto the lab. I feel a force downwards. But that's not actually a real force. So what I feel is a fictitious force. Einstein applied this to how we're living on Earth. We feel like gravity is pulling us downwards. But he said that this is actually a fictitious force. That the Earth is technically actually pushing up on us. But if gravity is a fictitious force, what actually causes things to accelerate downwards towards the center of the Earth? To answer this, Einstein stated that gravity is actually curvature in space-time. Normally, if particles want to move in a straight line, these distortions in space-time cause them to go towards the mass, like go towards the Earth. And this is the basic start to general relativity.